you can email me and say, Mr. Up, I don't understand what the teacher's saying. It does still a little bit. Profs don't like that too often. You have to ask, or you have to sort of watch that. Sometimes you can, sometimes you can't, right? They don't, like, I've been in classes where kids will take the micro cassette recorder and just hit the record button and put it on their desk while they take notes. They don't miss anything. But some profs will let you do it, some won't. It's just like, you know what, if I want to yell at a kid in my room, I'll cover the mics up and yell at a kid. Well, and you got to, some of them won't even, you know, like, the texting has gotten to a point where they won't let you bring computers in because kids are just using Facebook in class, right? So I would be, if I got to bring technology into my room, I'd bring a laptop like this and hit that encoder button and take notes while the prof's talking, right? And then you could hear the lecture going on while you're taking notes like me. Do exactly the same thing for yourself. But some profs are okay with it and some aren't, because that whole, kids have ruined it. Current kids have ruined it for future kids. That texting, email, twittering during class that's not on topic is become such a problem that the university profs won't let kids, like, they just drives them right up the wall, right? I was thinking about maybe eventually having a Twitter feed where if you don't want to ask a question in class, it's going to come over on the corner of my screen and go, okay, John wants to ask about this. Sorry, John, but I used your name for a second. John wants to ask about this. Okay, cool, I can answer the question. You don't have to ask the question in class. You just quietly do it via your Twitter feed or yeah, it makes it, I think it would be a neat way to ask questions or to get feedback from you guys about the lesson. That was a piece of dog crap. I didn't make any sense. Versus, hey, that was cool, thanks. Like one way or the other, right? It gives me feedback as well. Online polls. Be truthful. Truthful. It didn't make sense. What was that? Right? I kind of expect you guys to stand up to me and say, that didn't make any sense. Where's that coming from? Right? You guys are paying for this ultimately. Okay. Anyways, so you heard my rant about technology. So we used the notation dy over dx or y prime to represent the derivative of y with respect to x. But when we first learned about the derivative, it kind of looks like a ratio or a fraction. So to make it a bit confusing, we're going to define some things using the same notation but in a different way. We define delta x as a large change in x. We define little dx as a small change in x. Yeah, that's just how it's defined. That little d means delta x, just a small change. Yeah, the actual triangle means a big change in x. A small triangle means a small d means a small change in x. Well, it's just all relative. It doesn't really matter is what I'm trying to say. A large change in y, delta y, a small change in y, dy. It's actually, no, I'm not going to get into it. It doesn't really matter that much. But we're defining a new formula. Let y equals f of x be some differentiable function so we can take its derivative. The differential dx is an independent variable. The differential dy is given by the formula dy equals f prime of x times dx. Now, what really, the way I kind of explain it and show you where the formula comes from is you take the formula, well, what a derivative means, right? dy over dx is the same as f prime of x, yes? Yeah. Take this over to the other side of the equation like it's a separation of variables, like it's a differential equation from chapter 6, and you get, but we don't take the antiderivative, and then I say to you, hey, dy and dx are not derivatives, they're just little changes in y and little changes in x. And then I just say, if you don't like it, just use the formula. Because this is just the way it is. Okay? So find the differential dy. So what I'm asking you to do is to take the derivative. Take the derivative of that. So we want to know what f prime of x is. And it's 5x to the 4th plus 37. And then you just put it in the formula. dy equals f prime of x dx. So it's and you're done. Miss Williamson down in the office. But I don't know if she's printed it yet. What's f prime of x for this one? What? Cos 3x times 3, use the chain rule, and then put it in the formula, dy equals 3 cos 3x times dx. What we're trying to do, do you guys want a little picture of what's going on here? Okay, so what we're trying to do is, I don't know, we've got more room on the right. So we've got some curve, whatever. And we got this point, a, f of a. I want to go a little bit to the right. Oh, dx units to the right. And I'm going to go up to the curve, and that's f of a plus dx. And I'm going to compare, what I'm trying to do is compare how the tangent line compares to the real distance. That's all it's really talking about is how far off is the real distance from the experimental from the theoretical. There's the chemistry and physics terms. How far off the theoretical is from the experimental? Well, we're going to talk about that, yeah. Experimental minus theoretical over experimental times 100 or whatever. Yeah, same kind of ideas. Okay? Does that help? Okay. So here's the math example. Sorry, I don't do the chemistry example till later. The radius of a circle increases from 10 to 10.1 meters. How much does the area increase by? So you take the area formula of a circle, like your f of x, and you take its derivative. So a prime is 2 pi r. Yeah? So using the formula that I've been scribbling on the page, is dA equals a prime times dr. And dA equals 2 pi. And then somebody was talking to me in the last class about how do you know which r to use? It's the lower one. It's the one you're increasing from to the next one. So it's 10. And then dr is just how far you're changing by, a small amount. 0.1, yeah. So you throw that in your calculator, or you don't need a calculator for that. You just think about it for a second. You go 20 times 0.1 is 2, so it's just 2 pi. So an increase of 0.1 meters, it will increase the area by 2 pi units. 2 pi square units, actually. Now the true measure, or the true change, you actually have to do the area calculation. So you have to go, delta A is pi times 10.1 squared minus pi times 10 squared. Well, now you need a calculator because I can't do 10.1 squared in my head. I wish I could, but I can't. I think it's 102. 0.01 pi minus 100 pi. Linearization, yeah, it's kind of related to that as well, because we can actually measure how much your linearization is now off by using these ideas. So you get 2.01 pi. So how close is our estimate? Is that a good measure of an estimate? It's pretty good. Okay, flip the page. What? Yeah. Yeah. But we tend to go from the smaller to the larger, so that doesn't happen. Like it, well, or we're talking about, we're also talking about how much it changes by. Like, we don't care too much about the direction. Like, if it's just, is it a big change or is it a little change, and how much is the change? Because you don't say, when you say percent error in chemistry or percent error in physics, it's 2.3%. It's not negative 2.3%. We just know that it's the number that we're interested in, not the sign on the number here. Does that kind of make sense? Okay. Flip the page. So there's some formulas there. Absolute change. This is the one that we've been using. This is absolute change on the previous page. And then there's relative change, which is that whole theoretical, and I can't even do this one right in my head. Oh, experimental minus theoretical divided by theoretical. And then writing it as a percentage. Experimental minus theoretical divided by theoretical times 100. Right? I see, I don't remember that from physics. I don't do it very well. So what is the percentage change in the area in the circle in the previous example? Well, the area of the circle, the radius of the circle in the previous example was 10. So its area is pi times 10 squared, or 100 pi, right? So the percentage change is dA over A times 100. dA on the previous page was 2 pi. A on this page is 100 pi times 100. Mr. App, we're talking about a 2% increase, or 2% error, or 2%, not 2%, it's a 2% change. 2% change. Okay. And you think, geez, going from 10 to 10.1, it's not a very big change. Well, it's actually 2%. Suppose the Earth was a perfect sphere and we determined the radius of the Earth to be 3,959 plus or minus 0.1 miles. What effect would that have on the tolerance? So I have on our estimate of the Earth's surface area. Well, the surface area of a sphere is 4 pi r squared, so we could take its derivative. S prime is 8 pi r. And then we use the formula. ds equals S prime dr. Well, S prime, 8 pi times 3,959 times pi, I got there, r, dr. What's dr? 0.1. So throw that in your calculator, because I don't do that one very well either. 8 pi times 4,000 times 0.1. It's bigger than that. Times about time. 9950. 0. So what this is saying is if our measurement's off by 0.1 of a mile, or we know our tolerance for our measuring device is 0.1 miles, that their surface area calculation could be off by as much as 10,000 square miles. So you're thinking, what's 10,000 square miles? Well, that's Vancouver Island. It's like shrinking the it's like shrinking the Earth's surface down and cutting out Vancouver Island and sewing it together. Can you visualize that? So like 0.1 of a mile in a shape this big can be quite a large amount. Yeah? Like if we talked about how far we are from here to the sun, and we said the distance from here to the sun is 2.8 billion kilometers plus or minus 0.1 of a kilometer, and then I ask, what size or what is the area of the circle that the Earth spins around, it's going to be quite a large amount, because that 0.1 of a mile in that form you get what I'm talking about here? Riley? You know what I'm kind of getting at? Okay. It's just the size of the numbers cause the error to be very big. Okay. And then I thought I'd get all medical on you. So an angioplasty is a medical procedure where they stick a metal, basically, a fancy way of saying is a medical arm a medical device down your arm into a vein or an artery, generally near your heart, that's blocked with plaque, fat, cholesterol, right? So what they do is they stick this balloon inside of this wire mesh that goes down this metal tube that goes into your arm. Sorry for all the biology students because I explained this wrong. But then we put air into the balloon expands the wire mesh. The wire mesh expands your artery to let the blood flow through. Then they deflate the balloon, take the balloon out, take the wire mesh out, and they leave the wire mesh there because it stays permanent. And then they pull everything out, and then they sew you up, close your artery up and your heart. And it's called an angioplasty, and it helps people live. Because the only other option to fix this is to cut you wide open your ribs up, like, right? And go in there and cut out the section of the artery, take a piece from your leg, put it in your... Okay, which is less invasive? Do you know what I mean? Like you can go home from an angioplasty after a couple of weeks, or a week, or 10 days. You can't go from open heart surgery in like the recovery time is amazing. It takes you way longer to open you up and fix it that way than it does the other way, and it's cheaper. Hey? Okay, so the interesting thing is so we do this. We can't get rid of all the crap, but what we do is expand your artery wall a little bit. Can we expand it a lot? No. Everybody try and run too much water through a hose, too much high pressure water through a hose. What happens to the hose? Cracks, it splits. So you can only do this a little bit, right? 10%. So you're thinking, 10%. Expanding a little tiny artery, 10%. That's not going to help you that much. Let's find out. Dun, dun, dun. So we need to know what V prime is. And that's 4kr to the 3, 4kr to the 3. Yes? Okay, so dV is 4kr to the 3. Yes? dr. So I'm just using the formula across the top. Now what I'm asking you to use is the second formula in that system of 3 equations. The second formula says, I want to know the relative change. I want to know how that helps. Okay, how is that going to help me? So I'm going to use this one over here. So I'm going to take the calculation I just did, and I'm going to divide it by the V formula. What? Yeah, it's just, well, V equals, but it looks funny to V equals V. You don't have double equals in it. So what happens to the right-hand side of that equation? The K's cancel. The R's reduce. So you're left with 4 dr over R. So we'll just do a just cuz. Let's say R equals 1. What happens? You get 4 times 0.1 divided by 1 of the artery. Just some constant. It's a French physiologist, Jean Poisois. Jean Poisois? Poisois? I don't know. We'll get your French immersion. Poiseuille. They say Poi. How do you say that? Poiseuille. Poise. I want to say Poisel, but that's bad. Anyways, so you do that. What do you get? You get like 0.4. So a 10% increase in radius causes a 40% benefit, a 40% increase in blood flow. You increase, you just make that radius, you know, from 1 to 1.1, 1 millimeter to 1.1 millimeters, your blood flow increases 40%. So you've gone from a serious medical problem to a less serious medical problem. Yeah? Now, somebody throws up their hand and says, well, why don't I make it a 20% increase in radius, right? Okay, that's an 80% increase in blood flow. But how much do you really want to push? How much do you want to expand something that's really thin cells, right? Can you kind of visualize what I'm talking about here? Like, you take a thin piece of medical tubing to mimic what a heart, to mimic what an artery looks like, and then you inflate it. How much can you inflate it before it rips and tears or bursts? Right? Can you visualize kind of what I'm talking about here? So you want to be very careful when you start to do this with people, because then you're going to have to open them up to go in there and fix it. Okay. Okay, last one. In honor of Mr. Epp and Math 12s, you take your average grade 8 and you want to figure out how deep a well is, so you take them over to the well and you drop them into the well. And you measure with a stopwatch until you hear the splashing sound to guesstimate, you know, the depth of the well. Right? You can do this. This is your homework for the weekend, but don't do it with grade 8s. Okay, there's my disclaimer. I know tests, sorry. You can't find that grade 8 you don't like, take them over to the well and then drop them off. Okay, so you're not a very good stopwatch user, so you think you're only accurate when you hear the splash, you're not very good at hitting that stop button, so you're accurate to within 0.1 of a second. So I want to know, so the question is how much will that affect your estimate on the depth of the well? Calculus or depth. So, yeah, so anyways, D prime. What's D prime, kids? 9.8 T. Thank you for being appropriate with your units, Mr. Epp. I know, it's pretty awesome. So, DD, crappy formula used. Maybe we should make this a capital D. Make that a capital D. Okay. DD equals D prime DT. So, big D, DD equals 9.8 T times DT. Now, Mr. Epp, you didn't tell me how long you were timing for, so I'm going to make some times up. So let's say that takes grade 8, takes the grade, you think it takes them 2 seconds to hit the bottom of the well. So push, click, splash. Oh, cool, 2 seconds. Well, how much is your measurement off by? Well, it's 9.8 times 2 times 0.1. which is about 19.6. Is that right? Or 0.1. So 1.96. 1.96 meters. So your measurement could be off by as much as 1.96 meters. Okay, so you take the average grade 8 and you push them off the well and you 30 seconds, Riley? Okay. Splash. Cool. That took 30 seconds. 9.8 times 30 times 0.1. So the longer it takes, the greater the error. Okay? Did you guys ever talk? Probably didn't ever enter any discussions in science. Okay. So what do you get? What? 29.4 meters. So the time is increased, or sorry, because the time increased, your error is going to be off. Okay. Okay. No, it's not. Okay, yeah, because I mean, sound, I'm like, you're right, but I'm not going to. Okay, do we want to get all physics on it? You take a grade, so you take a grade 8, D equals 1/2 AT squared, so 9.8 times 30 squared. But the sound goes back up at a certain... Do you really want to get all... Well, then I'm not going to. Let's make it way more complicated than it needs. Yeah, I know. Anyways, that's it, folks. I put a couple of questions at the bottom for the kids that are doing the AP exam. Those are the ones that I would do for this section. No, I'm not testing you on it, but if you're going to do the AP exam, those would be the ones that I would make sure that I do and know that. On this won't be on a test. No. That's it. That's all. There is no more.